Welcome back, everyone, and I hope everyone's feeling okay. Today's lesson is on kinetic theory, and we're going to be doing 4 things in this lesson. Firstly, you'll be able to, hopefully, by the end of the lesson, state the kinetic theory for an ideal gas. You should be able to relate temperature to kinetic energy mathematically using a relationship. You should be able to list all the assumptions made in the kinetic theory of gases, and then differentiate between real and ideal gases. So state some exceptions. So the kinetic model of an ideal gas is a way of explaining macroscopic behavior. That means behavior in the real world, in the big world, using microscopic behavior, which is the behavior of particles microscopically. So you're using the behavior of individual particles on a microscopic level to explain some really big stuff in the real world. So what do we mean exactly by macroscopic real life behavior? Well, in terms of gases, it is kind of strange because we don't see gases in our day-to-day life, so we don't tend to think about them. But number one would be gas pressure. Gas pressure is a very important property of the atmosphere, for example, and we don't think about it, but it's actually a considerable amount. It's about 101,000 newtons per square meter, which is insane, right? So it's a considerable force per unit area. Secondly, we can look at the random motion of vapor trails or vapor from a power station. This weird random motion can also be explained by particle kinetic theory. So let's have a look at that theory in a bit more detail. The kinetic theory of gases is a simple model for the behavior of gases. And the model describes a gas as identical submicroscopic particles. They could be atoms or they could be molecules, all of which are in constant, rapid, random motion, right? So that's how gas particles move, constantly, very quickly, and random. Now, this random motion is something you might come across in chemistry, or you might have come across it before. It's called Brownian motion, right? It's an important phenomena because Brownian motion is basically the observed behavior of gas particles, demonstrating and proving that it is in fact random. It's not actually on the syllabus, but I would like you to take the time to watch these 3 videos later. I'm going to attach them to Classroom, although they are on the presentation as well. And just have a look at them because what these show are experimental evidence for Brownian motion. They're basically proof of the way that the particles move. Now, you don't actually see, it's impossible to see gas particles move, but what these experiments show you is what happens when very light and very small particulate matter, like ash, for example. Ash is a suspension. Ash and smoke is a suspension. It's just very, 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 very tiny little particles of paper or whatever's burning, right? So those are very light and small, and because they are being pushed around and bullied by the air particles around it, they move and in fact demonstrate and prove what the motion of the air particles around it are like. Okay, so it is a bit of an appendix. It's not in the syllabus, but I think Brownian motion is just a really nice demonstration to look at in understanding how gas particles move randomly. So apart from moving fast and randomly, they collide. Now, collisions are a very, very important part of kinetic theory because every time a molecule hits a surface, it creates a tiny force on the wall. And if you consider the considerable amounts of particles that are constantly hitting the sides of a container, that actually adds up to being an insane force. So if you consider that right now on your head, there is a force of 101.3 thousand newtons per square meter, right? That is an insane amount, but it's actually something that your body has evolved to cope with. Now, literally, you take that away, the pressure in your blood pressure has kind of evolved to balance it, right? To balance that pressure, and you'd probably explode if you took it away. I'm exaggerating, but there's a couple of good science fiction movies that demonstrate this fact, and I might attach them to Classroom just for effect. Yeah, so the average force creates a massive pressure, right? And that force is basically created by the collisions of the gas particles. Now, this theory, which states that a gas is a large number of small particles that move at very fast, at very high speeds, is very useful for making predictions, right? And modeling and explaining how things work in real life. But in order for that explanation to be completely sensible, you have to make some assumptions. Now, these assumptions are very important. They do come up fairly frequently in the exam. Basically, what we're assuming by this model is that we are using a very, very, very large number of particles. So something along the lines of 10 to the power of 18. We also assume that the particles are very small, right? The typical size of gas particles is 10 billionth of a millimeter, 10 to the minus 10 meters. Now, this is important because you're considering that they are point particles, and there's no interactions above just what would happen if you have an infinitely small particle. You also assume that they're moving randomly. But we've kind of mentioned that already, but there is no predictive aspect to their motion. We also assume that their speed is extremely high, right? So very, very, very high speeds. And we're talking several hundred kilometers per hour. Now, this is another really important one, that Newton's law applies. So what we're doing is we're assuming that we have still a Newton universe and that our collisions are elastic. That means that when these two particles collide with each other, they don't lose energy in that collision, which is just as well, really, because if every time two gas particles collided, they lost energy, then the entire atmosphere by now would probably have just like dropped into a big pile on the floor, because that energy loss over a considerable amount of time would be considerable in itself. And then we are assuming that there are no particles acting on between them, right? There's no forces acting on the particle except the contact force when there's collision, right? So they're not attracting positively or repelling negatively. They're completely neutral until they're in contact with each other, and then the contact force forces them apart. And now we're going to come to a second really important point, and that's the idea of an ideal gas. These assumptions describe what we consider to be an ideal gas. And it's not the only thing that we've looked at which describes an ideal gas, and we'll come back to that in a minute. But an ideal gas, by definition, is one where the assumptions apply. So all of these are in fact the case. Now, mathematically, the challenge in this section isn't particularly high because there is a relationship and you don't have to prove it. There is an interesting proof that goes with it, but it's not on the syllabus, and I'm not going to burden you with it now. Maybe when we get back to a classroom, I can go over it with you. But basically, the relationship between the kinetic energy and temperature is a proportional one. Now, you guys knew this already, but what we have is a constant of proportionality now, which I'm going to introduce, which is 3/2 times KB, which is the Boltzmann's constant. Now, that Boltzmann's constant is 1.38 times 10 to the minus 23 joules per Kelvin. And it's important to remember that temperature is in Kelvin, right? The temperature of an ideal gas in Kelvin is a measure of the mean random translational kinetic energy of the molecules. So temperature actually gives you a direct measure of how much kinetic energy the particles have. Now, the proof that I'm not going to do at the moment, what it does quite nicely is it links the gas laws, the relationships between pressure, volume, and temperature to this mathematical relationship for kinetic energy and temperature. So you can actually prove that PV equals nRT, this relationship, you can actually prove that it matches this one. And again, we will do that later on in the year. But mathematically, what you find is that Kb, Boltzmann's constant, can also be represented as the gas constant 8.31 divided by Avogadro's constant. So it's another way of expressing the same equation. Now, don't worry, because both of these equations are available in the data booklet, should you ever use them. I've included in Classroom a link to this simulation, right? It's definitely worth having a go. You're allowed to play about with the variables and look at the way that the gas particles behave under a bunch of different conditions. So spend 5 minutes playing around with this simulation, seeing as we can't do any labs at the moment. So finally, just to sum up, what do we mean by an ideal gas? And there are two ways of outlining it. The first one is that the assumptions for kinetic theory apply. And secondly, that the ideal gas equation applies too, that all the relationships, the proportional relationships associated with the gas laws apply to an ideal gas. So there are two justifications for what an ideal gas are. The theoretical, that's the whole assumptions and imagining gases as tiny little particles, and the practical, the empirical, which is what we do in the lab. These two describe ideal gases. But then we have real gases, just to complicate it. Basically, when in real life do these two things not happen? And it's pretty much the case in some very specific circumstances. There are usually real gases do actually behave like ideal gases. However, when the interparticle forces between the atoms or between the molecules become significant, right? Or if the particle size is no longer negligible. If you remember, these are two of the assumptions. One of the assumptions is that there are no forces. One of the assumptions is that the size is tiny, right? Insignificant or point particles. So when this is no longer the case, then you cannot say that your real gas is an ideal gas. And when does that happen? Well, you have really high pressure and you're forcing the particles together, like so that they have to be close together. If you're assuming a situation where you have really high density, which could happen because there's high pressure, right? Because you're forcing all the particles together. And if you have low temperatures, again, very, very low temperatures will force the particles to be very, very close together. And when the particles are very, very close together, their interparticle forces start to kick in, right? So basically, any situation where interparticle forces start to happen, and usually there's three situations: high pressure, high density, and low temperatures. One of the consequences of forcing particles together is that they change state, right? So at low temperatures, gas particles have low kinetic energy and there is some attractive force. And what happens? Things start to condense, right? A gas will start to become a liquid. It's not going to follow the gas laws. It's not going to follow kinetic theory if it's becoming a liquid, right? So an ideal gas cannot change state. And so therefore, if your gas is no longer following ideal gas equations, then what will happen to a real gas is it will stop. I've got a bit crazy now. It will stop doing these three things, and you'll find that your relationships are no longer linear. This, for example, is a picture of what real gases do in terms of their pressure and volume. Real gases versus ideal gases. As the volume becomes smaller and you force the particles together, things start to go a bit weird. So to sum up, at high pressures and densities, intermolecular forces become significant. Ideal gases do not condense, and real gases stop behaving like ideal gases at high pressure, high density, and low temperatures.